we have seen some of the applications of differentiation, including differentiation as a rate measurer, and we also saw the application of differentiation in analyzing a function to understand, intervals in which the function is increasing or decreasing. So we'll continue ahead from that point onwards today. Okay, so let's begin. Yeah, so before I further get into analysis of functions using differentiation, and through that we will understand about something called maxima and minima today, I also wanted to review one more thing. There are certain types of differentiation involving inverse trigonometric functions. If you've gone through the revision worksheets that I had sent, you will find there were a couple of questions based on that. So let's begin by seeing how to solve those kind of differentiations using chain rule. Okay, so differentiation of inverse trigonometric functions. Okay, as an application of chain rule. So first of all, what is an inverse trigonometric function? It is a function that is, you can say, the reverse operation of a trigonometric function. So for example, if we have y is equal to tan inverse of x. Okay. So this basically implies that x is equal to tan y. Or you can write it like this, that if we take tan on both sides, tan of y is equal to x. Okay. So please understand that y is equal to tan inverse x does not imply that y is equal to 1 by tan x. It is not to the power minus 1, though it looks suspiciously like that. It is inverse. Okay, so this is read as tan inverse of x. Okay. If we had y is equal to tan x to the power minus 1, okay, then that would imply that y is equal to 1 by tan x. Okay, so how does this work? Let's understand. So for example, suppose we have, okay, some quantity, let's say theta is equal to tan inverse of root 3. Okay. So from this we want to find out theta. So it means that tan theta is equal to √3. So the fundamental solution is that theta is equal to pi by 3 or 60 degrees. Of course, theta will also have a solution in the third quadrant, but if we are treating it like a function, then it should have a unique solution. So we will take the solution only in first quadrant. Similarly, for example, if we have okay, just try out these three questions. Then we'll move on to differentiation of inverse trigonometric functions. Yes, Adinath, very good. All three parts are correct. Ishan, good. The first part is clear, is correct. Yeah, you can give the angles in radians or degrees both. It doesn't matter. Okay. So I'm correct. Vaish correct for the first part. Anshul, your first part is correct. Just check the answer for the second part. Ishita, very good. Correct. Shayan, correct. Saurabh, correct. Raghu, correct. Okay, so let's solve this. So this is basically just factual stuff. Okay, you just understand that if something is given as sine inverse of 0.5, that means sine of that is 0.5 or half. Okay. So we will take the primary solution of this, which is pi by 6 or 30 degrees. Okay. Of course, it can also be 150 degrees or 5 pi by 6. But remember that when we are talking about this as a function, it should have a unique solution. Okay, so one particular value of the independent variable must give us a unique value of the dependent variable. So we take only the primary solution. Now, trigonometrically, of course, this is also equivalent to 5 pi by 6 or 150. But purely as a function, if we say x is sine inverse of some variable and that variable is 0.5, then we should take the value of x only as 30 degrees or pi by 6. Similarly, this implies that cos y is equal to 0.8 or 4 by 5. So you know that y is equal to 37 degrees. Okay. Or if you want to convert it, this is going to be quite a monster, but it will be like this in radians. So better to leave it in degrees. Similarly, this implies that cot of z is equal to 0.75 or 3 by 4. So that means z is equal to 53 degrees. So of course, you must be familiar by now, especially after doing a lot of questions in vectors, that a triangle, a right angle triangle with sides in the ratio 3, 4, and 5 has the smaller of the other two angles as 37. You just keep this triangle in mind, and you can see the solution of both this part and this part come from that. Okay, so most of you have got this correct. Okay. Now, just one thing you have to understand, that if you're talking about this as a function, okay, then it must have a unique solution. So we should not give the equivalent solutions in the other quadrants. We should just give the primary solution. Okay. However, if you are solving this as a trigonometric equation, then it need not necessarily be a function. So we can say there are multiple solutions. So if we are dealing with trigonometric equations as opposed to a function, then x equal to sine inverse of half will have solutions 30, 150, okay, then 390, okay, then 360 plus 150, like that. It will have the general solutions, okay, 2n pi plus pi by 6 and 2n1 plus 1 pi minus pi by 6, like that. But if you're talking about it purely as a function, then we will give only the primary solution. So that's just a small technical matter here. Okay. Now let's come to the main thing. Okay, you want to note down? Fine. Just finish. So finish writing this down, then we'll come to the main part of interest to us, that how to differentiate a function of this type. So let's start with our basic example, tan inverse x. So we want to find dy by dx. So what we can do here is to use chain rule. We can say that y equal to tan inverse of x implies that tan y is equal to x. So further it implies that differentiation of the left hand side with respect to x is equal to differentiation of the right hand side with respect to x. Now next thing we'll use the chain rule here. So the chain rule step will tell us that differentiation of tan y with respect to x is dy of tan y multiplied with dy by dx, and this side is of course differentiation of x with respect to this. So that is one. So next step, this becomes, as you all know from formula, sec square y into dy by dx. So dy by dx is 1 upon sec square y. Now at this stage what we want to do is, this is fine, but we want to express it in terms of x. So we'll use the identity that sec square y is equal to 1 plus tan square y, okay, and tan y is equal to x. So if you look at a mathematics book of advanced calculus, you will see that this is actually a formula that you learn directly also, that differentiation of tan inverse x is given by the formula 1 upon 1 plus x square. But here we don't need to, treat it as a separate formula and memorize another set of formulae for inverse trigonometric functions. At our level of basic physics, basic calculus for physics, when we come across an inverse trigonometric function, instead of treating it like a new formula, we can just use chain rule like this. Okay. So differentiation of the function tan inverse of x comes out to be 1 upon 1 plus x square. So just make a note of this, people, step by step. Okay. And after you make a note of this, try the next example yourself. We have y is equal to sine inverse of 3x. So you want to find dy by dx. Just try this out. Use the very same steps that we have done over here, but with the sine inverse 3x function. Yes, very good. You should be getting the answer of this. Okay. Yes, Parv, that is correct. But in the final step, you have to just express cos y in terms of x. So if you see, you know that sine y is equal to 3x, right? So then use the relation between sine y and cos y. So Pratham, Rishabh, Parv and Caleb, Anshul, all of you have to understand this, that dy by dx is 3 upon cos y, but then you have to express that cos y in terms of x. So to do that, you have to use the identity between sine and cos. That sine square theta plus cos square theta is equal to one identity. So let's review this, how this is done. So just that final step, how it will come, let's see. So we have this example now, that y is equal to sine inverse of 3x. Okay. So we can say that sine y is equal to 3x. So differentiation of sine y is equal to differentiation of 3x with respect to x. So now the chain rule step. So most of you have got to this step without any difficulty, I guess. Okay. But now the next step, I have to just express cos y in terms of x. Okay. So I have sine y is equal to 3x. So cos y is square root of 1 minus sine square y. So that is, so that's how we get the square root of 1 minus 9x squared term. Okay. So finally, we will express.
So we can square both sides. So can you square both sides?
It's like this. Okay. So just go through the steps carefully once. Let me know if there's any doubt. Very good, Caleb. Correct, Anshul. So there were a couple of questions based on this kind of differentiation in the revision exercises I had sent you last time before the test. Okay. Though in the test there was no question like this. In the test I tried to keep the questions based on the earlier worksheets as much as possible, so you had minimum difficulty.
Hello, sir. Can you hear me?
Okay, let's move on now. So as part of application of differentiation in analysis of functions, we'll see something very important today. We'll understand a new term called maxima and minima, and we will see how differentiation can be used not only to analyze the intervals where a function is increasing or decreasing, like we saw in the previous lecture, but also to analyze the maxima and minima of function. So this is typically called application of derivative, or another way of saying application of the process of differentiation. So you will understand maxima and minima of a function. But before that, for any given function, we learn two important terms. The set of values of x, that is the independent variable, okay, is called, you might have heard this term, the domain of the function. And the corresponding set of values of y, that is called the range of the function. The dependent variables values is called the range. Okay, so two new terms, domain and range. Let's understand this with an example before you write this down. So for example, we have, let's say, a function y is equal to x square. So you can see that typically the domain will be that x belongs to the set of all real numbers. Okay, but the range over here, the nature of the function is such that it is only non-negative numbers. Okay. But for example, if we have the function y is equal to 1 by x, then we can see that the domain, in the domain 0 is not allowed. So it is the set of minus infinity to 0, not including 0, union with 0 to infinity. And similarly in the range, you can see that 0 is not included. So y belongs to the set, again, minus infinity to 0, union with 0 to infinity. Okay. Or we can say that x belongs to all real numbers excluding the single number 0. And similarly, the range belongs to the set of all real numbers excluding 0. Okay. So this is what we mean by domain and range. Just make a note of this quickly.
Are we audible to you?
Yes, you can also try out this example. Yes, Pratmesh.
Sir, am I audible to you? Hello, sir.
It's minus sign. Yeah. Yeah, I'm not able to hear you. That's correct. Pratmesh, you can try again.
Sir,
Yeah, now I can hear you. Yeah.
sir, that is minus sign or negation sign just before zero.
It's minus sign. So what this sign here means now is that x belongs to the set of all real numbers minus the single number 0. So it excludes 0.
Okay, sir.
Sir, can you explain the examples again?
Yeah, so see what is happening now, that when we have the function y is equal to x square, the value of, so we immediately understand x is independent variable, y is dependent variable. Now here you can see that we can do this operation for any real number, because any real number's whole square is defined as another real number. So the domain
Yes,
of the
sir.
function becomes the set of all real numbers. But because the value of y is square of x, so we know that when we take negative numbers and square them, we get positive numbers. And when we square 0, we get 0. So the range, that is the set of values of y, only it ranges between only 0 and infinity. There is no value of x for which y will become a negative number. So we can see that
Yes,
the
sir.
set of values of the dependent variable y is only 0 to infinity, including 0. So the range becomes 0 to infinity.
Okay, sir.
Now, like that, you can see that for the function 1 by x, we can do this operation for all real numbers other than x equal to 0, because 1 by 0 is undefined.
Yes, sir.
But similarly, when we look at the range, there is no value of x for which y becomes 0. If x tends to infinity, y tends to 0. But there is no exact value of x for which we get an exact value of y equal to 0. Okay, na? So
Yes,
that's why
sir.
the range also excludes 0.
Okay, sir. Thank you, sir.
Now, like this, you'll see the next example I've asked to solve. This is a little more interesting, because square root of some function. So square root is only defined as a real number for non-negative real numbers. We can define square root of something as a real number. So y is real only for 4 minus x square being non-negative. So there are only certain values of x for which that happens, that 4 minus x square is a non-negative number. So the domain will consist of only those numbers for which that is satisfied. So it really becomes like solving an inequality, that 4 minus x square should be greater than equal to 0. Yes, very good, Akshat. That's correct. No, Anshul, I'll give you an example. If you take the value of x as 5, you can see y is not defined for that. Yes, Adinath, almost correct, but remember that 4 minus x square can become equal to 0 also. It need not be positive. It can be non-negative, that is, can become 0 also. So similarly, y can become equal to 2 also. Okay. And y can become equal to 0 also.
Yes.
Yes, actually your domain is correct. Okay, just the range you have to make the correction. Yes, Shiva is correct. Only you have to use box bracket. Okay, so let's look at this example. So we can understand that y is equal to root of 4 minus x square. This implies that y has a real number solution when 4 minus x square is greater than equal to 0. Okay. So that means x square is less than equal to 4, or x square minus 4 is less than equal to 0, or x minus 2 into x plus 2 is less than equal to 0. Or we can also say like this, that 2 minus x into 2 plus x is greater than equal to 0. Okay. Either this or this, both are okay. So now we can solve either of the two by the number line method. Okay. So for example, if I'm solving this one, I can see that minus 2 and 2 will become critical points, because for the factor x minus 2, anything less than 2 is negative, and anything of x greater than 2 makes it positive. And for the factor x plus 2, anything of x less than less than minus 2 means it's negative. So now I can see that the product of these two things okay, that is positive in this region, negative in this region, positive in this region. Okay. So this is the thing that I'm looking for. So this implies that x is greater than equal to minus 2, less than equal to 2. Okay. If you make a number line for this one, you'll get the same solution actually. This will also give you the same solution. So the domain of this function, we'll say is that x belongs to the set closed interval minus 2 to closed interval 2, or x is greater than equal to minus 2, less than equal to 2. Okay. Now about the range. So next thing we see that for x going from minus 2 to 2, x square, that has a value of how much? 0 to 4. So therefore 4 minus x square has a value of again 0 to 4 only. Okay. So that means y, which is square root of 4 minus x square, this ranges between 0 to 2, because basically you can see that y's minimum value will be square root of 4 minus x square's minimum value. So that is square root of 0. Okay. And y's maximum value will be square root of 4 minus x square's maximum value. So that is square root of 4, which is not plus minus 2 people. Okay, you must be sure about this. Okay, just 2. So from that you can understand that this is happening, and from that we can now understand that the range of the function is that y belongs to the set of all real numbers between 0 and 2, inclusive of 0 and 2. Okay. So finally, this is our domain and this is our range.
How we got x square belongs to 0, 4?
Because if x is ranging from -2 to 2, na, you can see x square's minimum value is what? 0. But maximum value is what? 4. Two square is how much, beta? 4, no? Similarly, -2 square is how much? 4.
Yes, sir.
So basically, x square will have a minimum value when mod x is minimum, no? So mod x का minimum value इस interval में कितना है? Between -2 and 2 is 0.
Okay, sir.
Got it, no? So whereas mod x is maximum value is how much? 2, because we are going only between -2 and 2. So accordingly, when we square x, the minimum value is mod x is minimum whole square, so that is 0. But the maximum value is mod x is maximum whole square, so that is 4. Or you just visualize the graph of y equal to x square, na? You will understand. We have done that graph before. No?
Yes.
Okay, so hope this question is clear to all of you now. Yes, very good, Rishabh and Adinath. All right, now just one more thing we have to understand, that when we talk about domain of a function,
Sir, can you scroll a bit?
yeah.
Sir, done.
Okay. Now about domain, one more thing we have to understand, that there is something called a natural domain for a function and something called a restricted or specific domain. It may be the natural domain. So what is the natural domain? It is the set of all values of x for which y is real. Okay. So example of that was this only, that y is equal to, okay, implies that this was an example of what we can say is a natural domain. But sometimes a restricted domain might be specified. Okay. So typically that happens in an application type of question. So for example, we are defining displacement S as a function of time. Okay. For a motion starting at t equal to 0 and ending at, let's say, t equal to 10 seconds. And that displacement is given as, let's say, 100t minus 5t squared. Now here you will see that if we had a function y is equal to 100x minus 5x square, the natural domain of this function would have been that x belongs to the set of all real numbers. Okay, but that is not what we are doing here. This is having here t is time Okay, and the time is having a specific domain with a restricted domain. So the domain here becomes the set of values for t only between 0 and 10. So t belongs to 0 to 10. Okay, and I'm assuming here that t was time in seconds, and suppose s is displacement in meters. Okay, so this is an example of a restricted domain. So typically when we apply functions in physics problems or sometimes even in maths problems, we have a restricted domain. Okay, so now the most important thing, that when the domain is restricted, accordingly the range also has to be restricted. So here this unrestricted function 100x minus 5x square would have had a different range, but now when I restrict the value of time between 0 and 10, then it has a restricted value of the range also. Okay, so we'll come to the point about the range later, but first of all, you understand that we can talk about two types of domain. So if nothing is specified about the domain in the question itself or in the specification of the function, like in this example, I've just given you the function. There was no condition given on the domain specifically. Then we have to take the natural domain of the function. So what is the natural domain of the function? It is the set of all values of the independent variable x for which we can define the dependent variable y. Now, of course, remember we are talking about functions in the real number domain. So when we can, when I say we can define y, it means that we can define y as a real number. You might ask that, okay, why can't y become a complex number? There's no specific reason, but the reason is that here we are talking about functions in the context of real numbers only. We are not talking about functions in the context of complex numbers. That's a different subject in mathematics. Okay, so for us in functions, all variables must be real values. They cannot become imaginary values or complex values. Okay, so only real number analysis is done. So the natural domain is only those set of values for x for which y is a real number.
So I think the restricted domain should be used in kinematics.
Can be used in kinematics, for example, yes, but it can be used in number of things. Like for example, if we are using it in some vector relation where one of the independent variables is the magnitude of a vector. Okay, so magnitude of a vector is a quantity without algebraic sign. Na? So accordingly, so various things we can use it in. But yes, kinematics is something obvious in which restricted domain is used, right? So now the next thing we are going to see is that the moment the domain is restricted, the range also becomes restricted. Okay. But first you can just make a note of
So
this
can you explain
example.
once again that why in this example the time is restricted with domain?
Because the example itself is defining displacement as a function of time for a motion that is starting from t equal to 0. So that means negative time doesn't make sense, you know.
Yes, sir.
Let's say, you know, we are doing some experiment now in which we are measuring displacement as a function of time. So when the motion starts, that's when I have clicked my stopwatch. So my stopwatch has started from t equal to 0 when the motion started. Now, suppose the motion started and 2 seconds later I started my stopwatch. Then I could have said that, okay, t equal to minus 2 seconds makes sense. Because even before my t equal to 0, the motion had existed, it had started. But here, the question is clearly specifying that I'm measuring time from the instant when the motion starts as t equal to 0. So that means t negative does not exist for me because the motion did not exist before that. And similarly, it's ending at t equal to 10. So clearly the physical situation that I'm applying the function to is dictating that, okay, the experiment is lasting only from 0 on the stopwatch up to 10 seconds on the stopwatch. So when I define any
So,
parameter as a function of time, I cannot, for me, negative time does not exist for the motion. And time after 10 seconds does not exist, right? So that's the logic of it.
understood, sir.
Yeah. Okay, so now the final important point you add over here, that when the domain is restricted, then the range also becomes restricted according to that. So for a function with a restricted domain, the range becomes restricted to. So then the range is defined by the same thing. It is the set of values of y for all set of, for the given domain. Okay, so it becomes the set of all possible values of y for the given domain. But now that given domain is a restricted domain. Okay, so for example, if we had y is equal to x square. So let's start with a simple example. Y is equal to x square, but given that x belongs to only, let's say, 0 to 5, then the range of this function will become how much? So the range of this function will become 0 to 25 only. Because the domain is restricted. So this is an example of a restricted domain.
So if it is specified that x is restricted between minus infinity and positive infinity, then too it will come between it will come in restricted domain or natural domain.
No, then you can, if the question, for example, said y is equal to x square, where x belongs to all real numbers, then okay, the domain is specified, but it's not restricted now because it's equal to the natural domain only. You understanding the point, Beta?
Yes, I understand it.
But for example, the interesting thing here is suppose the domain was specified as non-negative numbers, y is equal to x square, and it was given that x belongs to 0 to infinity including 0, then it's a restricted domain. But interestingly, the range is the same as what the range would have been for the natural domain. So various such combinations can be there depending on the function you are dealing with. Understood my point now?
Yes, I'm.
But generally speaking, when we take a restricted domain, most often what happens, the range also becomes restricted, unless it's a very special case like the one I told you. Okay, so let's just do one more example of domain and range with a restricted domain example. Then we'll move on to maxima and minima, and you'll understand what was the importance of understanding domain and range for that. Okay, so we have, let's say, y is equal to 1 plus sine square x. Okay, so we want to find the range for the natural domain for this function. Okay. And for a restricted domain, given by the condition that x belongs to 0 to pi by 3 or 0 to 60 degrees. So in the second part, if I specify for whatever reason that x is not going to be less than 0 and is not going to be greater than 60 degrees or pi by 3, then what is the range of values of y I'll give, given the relation is, yes, Raghu, that is correct. Restricted domain is typically used only in, so I mean in general also the purpose of functions is to apply it in the relationship between physical quantities in the real world. Okay. Other than pure abstract mathematics. But I think in abstract pure maths also generally we use equations rather than functions. The whole idea of functions is to be able to relate physical parameters. So it makes sense that that most of the time we are applying functions to real life applications of physical situations. So there may often be some kind of restriction on the domain. Okay.
Okay, sir.
Of course, there are certain situations where there won't be any restriction on the domain, but generally speaking, there in physical situations there will be some kind of restriction.
Okay, sir.
Yeah. Okay. Now just try out this question, all of you. 1 plus sine square x, both for the natural domain and for the domain 0 to 60 degrees. Find out the range of the function.
So for second B question, we have to only find the range, right?
Yes, come again, beta. What was your question?
For the B, a restricted domain X belongs to 0, pi by 3. You have to
Hmm.
only find the range because domain is given, right?
Yeah.
Okay, sir.
So natural domain, to anyway that sin x is defined for all values of x. So natural domain is all real numbers. There's no problem with that. The question is, what is the range when the domain is natural, or what is the range when the domain is 0 to pi by 3? Yes, very good. Akshat is correct. Pratyush correct. Oh no, wait. Akshat, your lower limit of the domain you have to check once. Huh?
Okay, sir.
Yeah, because see what is happening now, sine square x can never be a negative quantity. So that means y can never be less than 1.
That's why I've excluded 0.
Yeah, but for example, can it be 0.5?
Yes, sir.
नहीं हो सकता है ना, उसका minimum value कितना है, 1 है. You understanding the point?
Yes, sir.
So see, for the first part, what we'll do is we'll understand that for x belonging to all real numbers, okay, sine x, we know from trigonometry, cannot be less than -1, cannot be greater than 1. So therefore, sine square x is between 0 and 1. Okay. And therefore, y, which is 1 plus sine square x, okay, y's minimum value is 1 plus 0, and y's maximum value is 1 plus 1. So y is belonging to the set from 1 to 2. Okay, so the range is this 1 to 2 for x belonging to all real numbers, which is the natural domain. Okay. Now this will give all of you an idea about how to deal with the second part, where we are restricting the domain to only 0 to 60 degrees. That means we are restricting the values of sine square x. So first of all, we are restricting the values of sine x. So from that, how you can see how sine square x is restricted. And from that, you can see how the range is getting restricted.
Sir, could you explain the part that sine square x is greater than or equal to 0 and less than equal to 1? That sine
Sorry,
x,
but a little bit louder, please. Can I explain where sine square x is?
sine square x is greater than 0 and then less than 1. I understood that the sine x graph goes between 1 and -1.
Yeah.
And then
So now
sine
see,
square-
just think of sine x as a new variable z, let's say. ठीक है? तो आपका z कहाँ से कहाँ जा रहा है? -1 to 1.
हाँ.
So what about z square?
It will go from 1 to -1 square 1.
So see, it's z square, no? So it's like mod z's whole square, no?
Okay.
So mod z का minimum value कितना है? It's 0 because z is going between -1 and 1.
Okay, understood.
Understood, no? So it's the same thing, no? Like if x was going between -1 and 1, then x square is going only between 0 and 1. So like that, if sine x is between -1 and 1, sine square x is only going between 0 and 1.
Understood.
Yeah. Okay, so let's look at the answer for the restricted domain part. So many of you have got this correct. Okay. So we have to have a little bit of idea about the sine x. Okay, so if we take x between 0 to pi by 3, so we know that sine x is ranging between 0 to root 3 by 2. Okay, because we know the sine x graph. In the first quadrant, for example, sine x is like this. So from this knowledge of trigonometry, so therefore sine square x is between 0 and 3 by 4 or 0.75. So we can see that y, which is 1 plus sine square x, y's minimum value now is of course 1 plus 0, which is 1, but the maximum value is 1 plus 3 by 4 or 7 by 4, or we can write that as 1.75. Okay. So that for this domain, y's range becomes 1 to 7 by 4. So for this restricted domain, this becomes a restricted range. So now we come to another way of expressing the range. Okay. For a function y is equal to fx, if the range is, let's say, a to b, then y equal to a, that is the minimum value. You can say the lower limit of the range is also called the global maxima of the function. Sorry, the global minima of the function. The lower limit is called the global minima. The upper limit is called the global maxima. So in relation to maxima and minima, there are two specific terms called global maxima and global minima. And this is what they mean. The upper limit of the range is called the global maxima. And the lower limit of the range is called the global minima. So very simple, really, nothing to do with the shape of the graph and all that. It is just that for the domain of the function, the upper value that y reaches, okay, that is the global maxima, and the lowest value that y reaches, that is the global minimum. For example, in the above case, 1 plus sine square x, for the natural domain, we would say the global minima is 1 and the global maxima is 2. Okay, now apart from global maxima and minima, we will also see something called local maxima and minima. And to understand that, we will just first visualize some of the common graphs. Okay, so let's start with a hypothetical graph, okay, just one that I'm drawing for an imaginary function, a function that I've not given in terms of a formula. So suppose I have a function whose graph is like this, and the function is defined for a specific domain x1 to x2, and in that specific domain it has a specific range, let's say y1 to y2. So for some function, okay, the domain the range is y1 to y2. So in this particular case, we can see that the global maxima is equal to y2 and the global minima is equal to y1. So that we can already see. But now we have also these two very interesting points, like a peak in the graph shape at the point x equal to a and a dip in the graph shape at the point b. You can also see that y increases from x equal to x1 to x equal to a, and y decreases from x equal to a to x equal to b. So what this shows us that at the point x equal to a, the graph of the function has a peak point in its shape. Okay. So such a point where it has a peak, it is called a local maxima, because it's like, within a localized set of values, the function has reached a maximum. You can see clearly from the graph that this value of the function, whatever the y coordinate is at a, it is not the global maxima because its value is less than this. But at the same time, the function is sort of peaking there before it starts to dip again. So that is why whatever the value of the function is at this point a, we call that the local maxima. So therefore, we say that the function fx has something called a local maxima at the point x equal to a. Okay, and of course you will see very clearly that in terms of slope, it's a very easy thing to understand that at the point where the function peaks, the slope of the tangent should become horizontal because it's increasing right up to that point, and immediately after that point it's dipping. So the slope, if it's a smooth curve, and any natural function will be a smooth curve, so the slope has to become positive, smaller, till the slope becomes exactly zero, and then the slope becomes negative after that. So exactly at the point where the slope of the tangent becomes zero, that is where we can say with confidence that the function has reached that local peak. Okay, so that local peak in the language of maxima and minima, it is called the local maximum. Similarly, we will see that this point where the function dips just before it starts rising again after b, that point is called the local minima. So also y decreases from x equal to a to b, and again after that y increases from x equal to b to whatever that final x is. So that means at x equal to b, the graph has a like a dip, or is the bottom of a valley, that kind of situation. So in language of maxima minima, we say that y is equal to fx function has a local minima because again you can see that it's not, there are values of y which are less than fb. Okay, but in a small, in an immediate neighborhood over here, it's reached a dip point, so it is called the local minima at the point x equal to b. Okay, now you might have a lot of questions that what if this peak was above y2 and all that, what we'll say in that case. So we'll come to all those cases. Okay, but first just understand the definition of local maxima and local minima in terms of the shape of the graph. The term local maxima and local minima may or may not have anything to do with the global maxima and minima. It is just to do with the shape of the graph. Where the graph reaches a peak, we say there's a local maxima, and the graph can have any number of local maximas. It need not have only one local maxima and one local minima like I've drawn over here. It can have multiple peaks and multiple dips. It all really
So
depends on
local
the
max,
nature of the function. Yes.
so local maximum and local minimum are just for some specified interval of the graph.
No, the thing is, na, it is not about a specified interval as such. Na. It is about the shape of the graph in a certain region. Okay. So for the given domain, if we draw the graph of the function, and in that graph at a particular point, the function peaks. So it has the nature that is increasing and then decreasing. So wherever it changes its behavior from increasing to decreasing, at that point we say there's a local maximum.
So while
Understanding my point?
while finding the local and local minima and maxima, we have to always draw the graph, or there is another other
No,
method.
see, the thing is now from the graph you can see that what is the repercussion of this in terms of derivative. Okay, from the shape of the graph you can see that derivative of the function or slope is becoming 0 at a and again 0 at b.
Yes, sir.
No? So that means we can use differentiation to find the point of local maxima and minima. So even if I have a function whose graph I don't know, okay, but I've given the formula of the function, like a cubic function or power 4, any polynomial function, or like that function 1 plus sine square x. मुझे उसका graph नहीं पता, but I want to find points where there is local maxima and minima. I can just visualize, okay, that if there is a peak point, the slope should be 0. That means dy by dx should be 0 at that point. If there's a minima point, again at that point the slope should be 0. And again using derivative, I can also find which part of the domain the function is increasing and decreasing. So basically, by analysis of the function from its derivative, we can not only analyze the part of the domain where function increases or
Like
decreases.
so for a cubic function, we will get derivative in a quadratic form, and then by
Yes.
finding the value of x,
Yes, correct.
we can find the two local and maxima and
Yes.
minima, right?
So that's correct. So a cubic function will have a derivative which is quadratic. So if we find the points at which the quadratic derivative is 0, so that means we are finding roots of that quadratic equation. Now it may so happen that that quadratic equation does not have any real roots. So in that case, the cubic function, in spite of being cubic, it will not have any local maxima minima. It may be that the quadratic function that we get as the derivative has common root. That means it has only one point which is either local maxima or minima. Or it can be that it has two distinct roots, in which case one of them will be local maxima, one of them will be local minima. Understood now? Okay, so before we come to more specific things about derivative with respect to local maxima and minima, let's just visualize some more shapes and understand that there is no particular thing that we can say about global maxima and minima versus local maxima and minima. Okay,
Sir,
we
could
can
you
have a
just pull up
situation.
1 minute?
Yeah, I'll come back.
Done. Sir.
Okay. Okay, now for example, we can have a situation where the shape of the graph of the function just happens to be like this, that it's like this. Okay, so the function is, let's say, so this is a function which is defined for x belonging to the set from A to D. Okay, but as you can see from the graph, the way I've drawn it, the minimum value of y globally seems to be at this point. Okay, so FC is the global minimum, and the overall maximum value of y seems to be at this point, which is FB. Okay, but also this is f of A. This is f of C. And similarly, at this point, there is x coordinate D and y coordinate f of D. Okay. So now note in this function, what is happening is that the range is from here to here. Where y1 is equal to the value of the function at C and y2 is the value of the function at E. So these are our global maxima and global minima. Okay. But at the same time, you can also see that also the function has two peaks. Okay. Or local maximas.
Sir, so it means every graph has a unique global maxima and minima.
Yes, it has one value of global maxima and one value of global minima, which is unique. Okay, but it can have any number of local maximas and minimas, and the point at which it has the global maxima may also be a point of local maxima or may not be. It depends on the shape of the graph. Okay, so it has local maximas at x equal to b and sorry, there was one more point here actually. Let's say this point is E, and this is f of E over here.
Sir, so every global maxima is a local maxima.
No, not necessarily. No, that's the point I'm trying to make. In this case, it's happening. Okay, but visualize the previous graph I had taken there. That was not happening, right? So this function
Yes,
has
sir.
two local maximas at x equal to b and x equal to e. Okay, and it has a single local minima.
So the range might change, right? If E is added.
Sorry, the range?
Range should change. X belongs to A to E in the example.
नहीं, but range क्या है बेटा? Range is the lower limit of y to the upper limit of y, na? You understanding?
Okay. Yes, sir.
So actually the function's y coordinate is, it's starting from fa, but it's coming down below fa, na, at some point of time. So the range is having a lower limit that is less than fa, which is in fact y1. You understanding?
Yes.
So in this case, what is happening? The global maxima actually coincides with one of the local maximas. Oh, I've written this in reverse. This is the global minima. See? So C is the global minima. And at B, we have the global maxima. Now this global maxima node, it is coinciding with this point. It coincides with local maxima at x equal to b. And similarly, the global minima, it coincides with the local minima. In this example, this is what is happening. Okay. But of course, it may not be like this in every example. Okay. So that is where, if you compare this with, let's say, another graph like this one, like let's say this graph is like this. Now in this graph, you can see that at this point, we are having both local and global maxima. Okay. But at this point, let's say x1, we are having global minima only. And at this one, we are having local minima only. And again, at this point, we are having neither local maxima nor global maxima. It's not a significant point in that sense. So we can see that now x equal to x1, y equal to y1 is the global minima. And it is not a local minima. Whereas at x equal to b, we have a local minimum, but it is not global. Sorry, local maxima. Is that? No, it's local minimum only, but it is not global. Okay. And the point x equal to x2 is not significant at all, other than the fact that the domain stops at x2. Okay, so have you understood this point, that in general, there may or may not be any connection between global maxima and local maxima, and global minima and local minima. They are two separate things. The definition of global maxima and minima are the upper and lower limit of the range of the function. Whereas the definition of local maxima and minima is more to do with the shape of the graph. It doesn't matter where the function is going up to overall. Globally, it doesn't matter what the maxima is, or globally, it doesn't matter what the minima is. What matters is that the graph of the function, if it is peaking at a point, then there is a local maxima at that point. If it is dipping at a point, then there's a local minima at a point. And a function can have any number of peaks and dips, and any one of them may or may not be the global maxima, or may not be the global minima.
Sir, so every global maxima minima are local. Every global maxima minima are local maxima and minima.
Sorry, come again, beta. Every global maxima and minima
Is local maxima minima.
No, no. See the graph I have drawn on the right side. उसमें क्या हो रहा है? Global maxima is also local maxima, but the global minima is not a local minima. You seeing now?
Yes, sir.
Or the graph that we had seen above, when we saw the definition of local maxima and minima, In this graph, you can see that the global maxima and minima are altogether separate. They are not points where there is peak or dip. So y1 is the global minima, but it's not a point of local minima. Y2 is the global maxima. It is not a point of local maxima. Understood now?
If there is no peak or dip, it can't be called local.
Yes. Now, the shape of the graph has to be such that it's a peak for it to be called local maxima, and it has to be a dip for it to be called local minima. And how do we recognize a peak and a dip? Either from if you know the graph of the function, or otherwise by analyzing the derivative of the function. If the derivative is switching from positive to negative, that means there's a peak at that point. Now just visualize the tangent, how it is changing as you're going through the point B, for example, in the first graph over here. Now the slope of the tangent is positive before B, but at B it switches from positive to negative. So it goes from positive to 0 to negative. Similarly, at the C point where we have the local minima, the derivative switches from negative before that to positive after that. So at C, the slope of the tangent is 0.
Sir,
Yes.
sir, why A is not the local minima?
Which graph on the left hand side?
Yes, on the left hand side.
हाँ, because देखो A पे dip नहीं है ना बेटा. A पे slope continuously positive है ना.
Okay.
If you draw tangent at the point A, is it a flat line? No, na.
No, sir.
Whereas look at the point C. If you draw tangent particularly at the point C, it will be a flat line.
Yes.
So remember that local maxima and minima has to do with shape of the graph. It should be a peak or a dip. Whereas global maxima and minima has nothing to do with the shape. It might be a point where there's a peak or dip. It might be another type of point also where there's neither peak nor dip. But it has to do with value.
So then we can say that every global maxima or minima is the local maxima and minima.
No, we cannot say, na, beta. That is the point I'm making. See, in the second graph on this page, on the one on the right, your local maxima is coinciding with global maxima, but your local minima is not coinciding with global. Na?
Okay, then it depends upon the peaks or the depths, we can say like that.
Yes, it depends on the specific nature of the function. So let's look at a couple of examples of functions, actual functions, and not ones for which I've just drawn an imaginary graph. Okay, and let's understand how this is happening. But before that, one more point you can note down is about the slope of tangent. So if the graph has a peak at a particular point, okay, so for a local maxima at x equal to a, what is the condition that slope of tangent at x equal to a should be 0? So that means f prime of a should be 0. Okay. So as you can see, if I draw tangent at this point, should have slope equal to 0. But at the same time, if I draw tangent at some point before this, it should be having a positive slope. And if I draw tangent at a point after this, it should have a negative slope. Okay. And the slope should be changing from positive to negative as x goes past x equal to a. So in other words, we can say that f prime at some point a minus delta x should be a positive quantity, and f prime at a plus delta x should be a negative quantity, because I'm treating this point as e minus delta x because it's before x, before a on the graph, and this point is e plus delta x. So the behavior of the slope you can see. Okay, so at local maxima, okay, f prime x switches from positive to 0 to negative. And at the point where it becomes 0, that is the peak point. Now, similarly, if you're talking about local minima, it has that opposite behavior. So this is the point x equal to b. The slope is equal to 0 at this point. But before this point, the slope is positive, sorry, negative. And after this point, the slope is becoming positive. So at a local minima, f prime x switches from negative to 0 to positive, and where it has become 0, that is the dip point. That is the point where the function has the local minima. And by f prime x, we also mean slope of tangent. So this is how, in terms of derivative, we can recognize where we have a local maxima and where we have a local minima.
Sir, can you please again explain how is slope changing from negative positive to negative?
Sorry, how is slope?
How is slope changing from positive to negative? Can you please explain it again?
See the shape over here at the dip point. If you draw tangent before the point where it has reached the dip, the tangent has what kind of slope? You can see it has a negative slope, the blue colored line here in this graph.
Yes.
Following now? Whereas cross the dip point to somewhere here, and the slope of the tangent, like the green tangent over here, has what kind of slope? It's positive.
Yes, sir.
Okay, so let's understand all these things by now using an actual example of a function. Let's take the function for x belonging to all real numbers. Now we want to find local maximas or minimas for this function. And we want an approximate graph of y versus x. Okay. So first thing we see while analyzing this type of function is the derivative of the function. So we can see that f prime x, or the derivative, is how much? 3 minus 3x square. So that is 3 into 1 minus x into 1 plus x. Okay. So straight away from the derivative, we can understand that the function is alternately increasing and decreasing. If we see the number line, we can see that there are critical points 1, or rather -1 and 1 on the number line, because the derivative is the product of two things: 1 minus x, okay, which is positive for x equal to 1 and becomes negative the moment x is greater than 1. Okay. But also we can see it's 0 at 1. And then there is 1 plus x, which is negative the moment x is less than -1, but positive as long as. So from this now we can see that the derivative, which is 3 into 1 plus x into 1 minus x, the derivative has this behavior that it is negative here, positive here, and then again negative here. So from this derivative, what we can say about the function itself, the function is decreasing, increasing, and decreasing. Okay. So we can understand that the behavior of the function is going to be something like this. And this point is going to be x equal to -1, this point is going to be equal to x equal to 1 because the slope is negative here. The slope is positive here. This, oh sorry, the slope is negative here, positive here. And then again negative here. But specifically, yes, but
Sir, what the f prime x will be between minus root 3 and plus root 3.
minus root 3 and plus root 3. F prime x you're asking.
Yes, sir.
So minus root 3 to yahan pe beta, it's like minus 1.732 and plus root 3 is over here. So the slope is changing now. Between minus root 3 and minus 1, the slope is negative. Then again between minus 1 and 1, the slope is positive. And then again between 1 and root 3, the slope is negative. Got it now?
Sir,
How did you get the
that,
point root 3 beta? Sorry?
Sir, because 3 minus 3x square, so if we like separate that, it can be root 3 minus x and root 3 plus x.
No, beta
root
3
x.
minus 3x square hai na? Root 3 kab aata? If it had been 3 minus x square. Just follow this step once. What is the differentiation of 3x? It's 3. But what is the differentiation of x cube? It's 3x square, na?
Yes.
So 3 is common here, na beta? Understood, na? What is now?
Yes, sir.
So what I've shown on the number line, you can analyze over here that f prime x is negative for x belonging to minus infinity to minus 1. Okay. Then f prime x is becoming 0 at x equal to minus 1. Then again f prime x is positive for x belonging to minus 1 to 1. Okay. And then again it becomes 0 specifically at x equal to 1. And then again f prime x becomes negative for x belonging to 1 to infinity. So now if we analyze here, what is happening? The function is decreasing. Here the function is increasing. And here the function is again decreasing. So obviously at this point, it's reaching a dip or it's having a local minima. And at this point, the function is reaching a peak. So it has a local maxima. Okay. So this is not a graph yet. This is just the sort of, you can see the trend of the function, how it's behaving. It decreases up to minus 1, goes through a dip at minus 1, then increases from minus 1 to 1, passes the peak at 1, and then again dips. Now, little bit more analysis and we can convert this trend of the function into an approximate graph. But as it is, you can see we've already got a lot of useful information. We have got the intervals in which the function is increasing or decreasing, that is these 3 intervals, and we have got local minima and local maxima. And it just so happens that this function has one local maxima and one local minima because it's a cubic function. Had it been any different type of function, it might have had different number of local maximas and different number of local minimas. Okay. Any combination is possible. Okay, so we will end the lecture here today because people in Ramshed Thakur are, I think, having a school lecture now. Okay, so we will pick up from this point in the next lecture. Okay, so the second part of this question, the approximate graph, you can just try out as a homework exercise when you are revising today's lecture. I'll be sending you an assignment also for today's lecture separately. Not a revision assignment, but an assignment based on what we've learned today.
Sir,
All right, people. Yeah.
can you send questions from module also?
So from where, better?
From module like
Yeah.
Question-
Module like
question
most of the differentiation questions you can complete now. Yes, Parv, you have some question, better?
No.
Okay. Okay, so that's it for today's session, people. Wish you all the best. Thanks for attending. I'll
Thank
send you a
you,
list
sir.
of questions from the module which you should complete for differentiation as well as an assignment. Okay.
Thank you, sir. Bye, sir.
Thank you,
Okay.
sir. Bye.
Thank you, sir.
Thank you, sir. Bye, sir.
Okay. Bye, people. Have a nice day.